So these are typical questions you should expect on Wednesday. What is pH of following? The first example is perchloric acid. You should know your strong acids versus weak. This is example of strong, therefore it dissociates 100%. It gives you hydronium, HO3 plus perchlorate. Now we are looking for this species. Its concentration is same as concentration of your acid. Therefore, pH is easily calculated as negative log of hydrogen or hydronium. So it's negative log of 0.1 and it's 2.0. That's your pH. The next example is sodium hydroxide. As you're looking for pH, realize it's a strong base. Dissociates 100%. This time we'll give you sodium ions plus hydroxide ions. Now you will find pOH. This is how you get tricked usually. So first pOH, then subtract from 14 to find pH. So concentration of your base is same as hydroxide. So what you can calculate is pOH, which is negative log of 0.15 mole per decimeter cube, and that becomes 0.82. Subtract from 14, pH comes to life. 14 take away 0.82, and that's 13.8. The next example is methylamine. Now this is a weak base. You should know it by now. All ammonia and amines are weak. So when you add it to water, you will have partial dissociation, equilibrium. This is your base and this is your acid. H2O behaves as an acid. So CH3NH2 borrows one hydrogen from water and becomes NH3 positive plus OH minus. Then again we find concentration of OH, pOH, and then pH. But since it's equilibrium, we need equilibrium ice. Initial change equilibrium, we write it in one shot, 0.5. Take away x moles of products come to life. Then since it's a base, we need Kb, which is products x squared divided by 0.5 O minus x. Go to your IB data booklet and Kb of methylamine comes to life, which is rather pKb is given to you as 3.34. So Kb is nothing but 10 raised to negative pKb, and it's 4.6 times 10 to minus 4. Now we are going to write our assumption or approximation in order to avoid quadratic solution. Since Kb it is much smaller than 1, you can say the denominator 0.5 take away x is nothing but 0.5. Life gets easier, so your Ka, which was 4.6 times 10 to minus 4, is simply equal to x squared divided by 0.5. X is your hydroxide concentration, and it's this time square root of 0.5 times 4.6 times 10 to minus 4. pOH is negative log of x. Now let's just calculate what this x value is, and this x is 0.015. 0.015, and when you do that it's 1.82. Finally pH is 14 minus 1.82, and it's equal to 12.18. The next example is a weak acid example. Plus water dissociate partially. This time you have acid, water behaves as a base. So the acid donates a proton and forms methanoate plus hydronium ion. We need to bring concentration of hydronium, we take negative log. Since it's weak acid, we go after ice. 0.5 mole per decimeter cube minus x, and x comes to life. It's acid, so we need Ka, Equilibrium expression is x squared products over 0.5 minus x. We go to the data booklet. pKa of methanoic acid is given to us in the data booklet, which is equal to 3.75. We find Ka, which is 10 to negative 3.75, and that's 1.8 times 10 to minus 4. We make our assumption. Ka is much smaller than 1. Therefore, denominator 0.5 minus x simply becomes 0.5. No more quadratic, it's just a square root. So we can say that x, which is our concentration of hydronium, is square root of initial concentration times Ka square root times 1.8 times 10 to minus 4. And when you do that, you get a tiny number, 0.00949. Therefore, pH is negative log of that, 949, and that is equal to 2.02. Final answer. The next example is you have a solution that you're mixing ethanoic acid, weak acid, and sodium ethanoate, sulfuric acid. So this is a buffer problem. Since it's an acidic buffer, we just write acid equation, and that's sufficient. Equilibrium. CH3COO minus, which is same as sodium ethanoate. So this is where the salt is adding another concentration. Therefore, you have a buffer. Plus H3O plus aqueous. Now, if you do ice, you will do 0.005 minus x, except for sodium ethanoate. Now you also have a value. It's no more 0 plus x. It's rather number plus x and x. You can solve it old-fashioned, or you can simply plug it into Henderson-Hasselbalch, which pH equals pKa plus log of your salt over your acid concentration-wise. So in the numerator you have CH3COO, in the denominator you have CH3COOH. Then we go after pKa of ethanoic acid in the data booklet. pKa of CH3COOH is equal to 4.76. So pH equals 4.76 plus log of our salt concentration is 0.0025. Our acid concentration is 0.005. So pH, when you do the log, it becomes negative 0.3 is equal to 4.46. An acidic buffer came to life. The next question is also a buffer question. This time they want to know the mass of your salt when you put it in 20 cm cube of 0.5 molar weak acid. Then again, I write the equation for weak acid. Although for this question you don't need the chemical equation, but it's a good practice. Equilibrium comes to life, CH3COO plus hydronium. Then I go after Henderson-Hasselbalch. pH equals pKa plus log of salt over acid, CH3COOH. This time the salt, I also put my potassium, so eventually you realize that these two species are the same. Potassium is spectator, but here I need to include it into my molar mass to find mass. Now if you look up pKa of ethanoic acid, is also 4.76. IB usually does that. Gives you values that you have easy time to crunch or calculate. So we want the pH to be 4.76. Our pKa happens to be 4.76 plus log of concentration of the acid is given. I put in denominator. Concentration of the salt I don't have. Put your variable x or however you phrase it. Now the question is, when does these two quantity equal to each other? When the log is 0, log of 1 is equal to 0. So from here you can say that concentration of the salt is equal to your denominator, which was concentration of the acid, and is equal to 0.5 mole per decimeter cube. We also have the volume of the acid or the solution, and you know that concentration is moles over volume. So we can find moles, which is concentration times volume. So moles of the salt is 0.500 times the volume converted to decimeter cube. So it's 0.020 decimeter cube. When you do this, you simply get 0.010 mole. Now to find mass, you need to multiply moles by molar mass. So it's 0.010 multiplied by, now you have to calculate, so this is 39.1 plus 1 carbon 12.01 plus 3 hydrogen 3.03 plus another carbon plus 2 oxygen 32. When you add it up, you get about 98.15 grams per mole. And when you multiply this, it becomes 0.9815, which I rounded to 2 grams of potassium ethanoate. So that's the amount of salt you need to put into this solution in order to have a buffer of 4.76.